Hello class, this is Craig, coming from my dining room. I wanted to send you a couple videos this afternoon because I realized I didn't quite do a great job this afternoon. I totally bypassed one important example in my notes, and the other one I know was new to you, and so I wanted to go over it. What I didn't realize, even though until Emmy reminded me, was that in this section, 14.3, I'm doing things differently than in the book. In the book, the author uses the Appendix D and has kind of a crazy method. It works, but it's not exact, and it's not, I think, as straightforward, as good a method as the ones that I showed you today. So I am going to hold you accountable for this information on the quiz. So let's try it. Let's start out with problem, let's see, I'm in 14.3, and this is problem number 3. It says we have a principal of $3,600. We have a maturity value of 48, or compound amount I should call it, right? Yeah, that's what the author uses. Same difference. 48, 24, oops, 34. And let's see, interest rate is 10%, and we're compounding semi-annually. And you did that backwards, didn't I? Okay, and let's see, 10%. Oh, and we want to know how long will it take to grow 48, 23, 34 from 3,600. Okay, well this is one of these problems where we need to use either the log button or the natural log button. The nice thing about this whole chapter is that we have used the same doggone equation for the whole thing. Well, I guess we had that effective interest rate, but basically we've been using this guy a lot. We started out simple, just calculating compound amount or maturity value based on a given rate, and let's see, an M value, which we got from the semi-annual or whatever statement was that determined how often we're compounding. And let's see, N we multiplied by the number of years and used M. You know all that. But in this problem, we are looking for time, and time is tied in the letter N. So let's start the problem the same way we do every one of these. First we say, what's M? M is the number of compounding periods per year, and this is semi-annual, so M is equal to 2. Which means the nominal rate, 10%, is going to not end up being the periodic interest rate. We take our nominal rate divided by M, and we see we're going to be using 0.05, a 5% interest rate in our problem. Okay, and finally, N. What's N? Is M times the number of years. And we have, well, years is what we're looking for, isn't it? Yeah. What do we know, though? We have M equals 2, and that will be important. We'll come back to that one. We say N equals 2 times the number of years. Okay, so let's begin our problem now. We can plug in what we know. Okay, M. I've got 48, 23, 34 equals our principal, 3,600 times 1 plus I, which is 0.05, raised to the n. Again, this is the problem where to get that exponent, we have to undo this exponent, and we use logarithms or natural logarithms to do that. First of all, I'm going to divide both sides by 3,600. 48, 23, 34 divided by 3,600 equals, I can add those two together, 1.05 raised to the n power. Alright, now here's the trick that we do. We either take the log of both sides or the natural log. It doesn't matter which we use, but if we use logarithm on one side, we've got to use logarithm on the other side. If we use natural logarithm on one side, we need to use natural logarithm on the other. Now, our BA2 plus only has a natural log button, so I'm just going to use natural log. And what I'm doing is, I told you in class that this natural log is a transformation. It's no different than when we say we have to add the same number to both sides of an equation or divide by the same number. So I'm just going to take the natural log of not just one side, but of both sides. So I'm taking the natural log of the entire side, which means I better take natural log of that entire quantity equals the natural log of this side, 1.05 raised to the n. And now here's the neat thing. We know, or I explained in class that, I probably should have given you a little equation for it, but when we take the natural log of a number, if that number is raised to the power, it's the same as bringing that exponent down and multiplying it by the natural log of the number without the exponent. Whoopsie. So all I've done is taken the n, put it out front, multiply it by the natural log of 1.05. And now what I'm going to do is divide both sides of the equation by the natural log of 1.05. And so I will have ln of this thing that's hard to write, 482334 over 3600 divided by the natural log of 1.05. And that is going to equal n. Now I've done that math, and you can pause the tape video and do it yourself. What I end up is that n equals 5.999999, and I don't know how many nines, roughly 6.0 if we do rounding to 1 or 2 decimal places. And that's cool. It looks like, oh, it might take n years to do this, but wait, there's more. No, remember that n is 2 times years, so really this is twice the number of years. So I'll just forget about n right here for now, and now I'm just going to solve this equation. I'm going to divide both sides by 2, and I'll have 6 over 2 is the number of years. And so the number of years it takes to earn, well, let's see, to grow your money from 3,600 to 4834, 2434, or whatever, is 3 years. But there was the trick at the end there. Knowing because we had semiannual compounding that n was 2 times the number of years. Okay, I hope that helps. I'm going to save this one, make you a second one.